So let's talk about sound today, sound waves. So uh, let's talk about the nature of sound waves first. So sound is a mechanical longitudinal wave, meaning it requires a material medium and propagates through compressions and rarefactions. Unlike electromagnetic waves, sound cannot travel in a vacuum, although particles oscillate about their equilibrium position. There is no net transport of matter, only energy is transferred when we are talking about sound. Let's talk about energy and power in sound waves. So as a sound wave propagates, it carries energy through the medium. And the rate at which this energy is transmitted is called power, which is measured in watts. However, power alone is not usually enough to describe how intense a sound is given at a location. For that, we are going to introduce what we call sound intensity. Sound intensity is defined as the power transmitted per unit area, perpendicular to the direction of what? Of wave propagation. So we are going to describe this by writing this equation or formula. So sound intensity, which is represented by capital letter I, is equal to power over area. So this is the formula we are going to usually use when we are finding sound intensity. So it's a power over the surface area. So it is measured in watts per square meter. Notice that intensity depends not only on the source power but also on how the sound spreads through the surface. Let's talk the spherical sound waves. So a point source of sound radiates energy equally in all directions. This is going to form what we call spherical wavefronts. So the surface area of a sphere we know that the surface area of a sphere is equal to 4 pi radius squared. This is the surface area of the sphere. So when we apply this formula, which is sound intensity is equal to power over area. So this is going to be power over 4 pi radius squared. So this is the formula we are going to be using because the surface area of the area of the sphere is 4 pi radius squared. So as we can see this formula tells us that sound intensity decreases with the square of the distance for the source. So this just explains why sound becomes weak as you move further away from the source of sound. So as you are going to be moving in your studies or lectures, you are going to hear this word decibel scale. So human hearing does not respond linearly to intensity. Instead, it responds logarithmically, which leads to the decibel scale. So this decibel scale, we write it like this. So they are going to ask you, can you convert that sound intensity into decibel scale, or can you calculate the sound intensity in decibels? So this is the formula we're going to be using, which is 10 log 10 here, then intensity, which is final intensity, over initial intensity. So this is the formula we are going to be using, where the initial intensity, this is the threshold of hearing, which is 1.0 times 10 power negative 12. So this is the formula we are going to be using when we are going to do some examples and we are going to see it. So this is the formula we are going to be using. So all you need here is the intensity. When you know the intensity, you can just plug those values on your calculator and you find the sound intensity in decibels. So let's do an example. For example, our intensity is 1.0 times 10 power 5. Can we change this in in decibels? So we are just going to plug everything. 10 log 1.0 times 10 power 5 here over that one, which is 10 power negative 12. We just punch on the calculator. What are we going to find? When we solve that one, we are going to find that 170 decibels. So that's how we do it. They can also ask you that you have sound intensity in decibels as 170 dB. Can you find the intensity, sound intensity, just the normal one? So you just go on the formula. 170 is equal to 10 log 10 here, then I over I initial. You just make I the subject to the formula, and you'll be able to find the same value of I which we had earlier. Talk about speed of sound. So speed of sound can be different, for example, in air, in solids, and also in liquids. So let's talk about in air. So at 0 degrees Celsius, the speed of sound in air is approximately 331 meter per second. So speed is approximately 331 meter per second. So as temperature increases, the speed of sound increases according to the formula, which is V. So this is the formula we are going to be using to find the speed in air. So which is 331 plus square root of T over 273K. There is a K there. So we are going that when we simplify this formula, it's going to be in this way: 331 plus 0.6 T. So this is the formula we are going to be using whenever you see temperature, whenever you see the formula of whenever you're given to calculate the speed in air, you use this formula. So this temperature is just a temperature, for example 50 degrees what, but you are going to just change it in Kelvin so that the units are Kelvin. So this is the formula we are going to be using. What about solids? So solids, for solids we are going to use this formula: speed is equal to the square root, we write y over, so this means y mean Young modulus, and that one, the P means density. So Young modulus over density. This is how you find the speed in what? In solids. So ladies and gentlemen, this is the end of the video for part 1 when we are talking about sound. So this was just the introduction. Next time we are going to talk about important lesson in sound, which is Doppler effect and other things like standing waves, beats. So just subscribe and like so that you may watch the next video. So bye for now.